Hello, today I'll walk you through the implementation of Read Your Write session guarantee on top of eventually consistent system. The implementation will be based on an article which is on the screen, session guarantees for weekly consistent replicated data. It's a very good article and I definitely recommend reading it, but today we will cover the information related to Read Your Rights. My name is Ivan Fedyanin, and on this channel I am doing series of videos about distributed systems. Let's start with short recap what the Read Your Rights session guarantee is. To find more complete explanation, just watch my video about client-centric consistency models. On the picture we can see distributed storage system which consists of 3 servers. There is replication happens between the servers, but for now we don't care which exact type of replication happens, and we just consider that this is eventually consistent system. It means that writes made on one server will eventually go to all other servers. First, client starts a session, depicted with a red circle here. Then at time t1 client make write to server 1, and then at time t2 it makes the read from server 2. The read your write guarantee requires that during the read client gets their own write in scope of that session. Notice that reads made out of the session, they don't have the same guarantee and they don't have to return previous writes. The simplest implementation of read your rights would be just to use the system in non-distributed way. On the picture it's shown with links of specific color that connect a client with a specific server all the time. In that case, each client is always connected to the same server, and it means that there are no anomalies because client makes writes and reads from the same server. And we don't have a distributed system, and we don't need to do anything special to support session guarantees because they are automatically supported. And sometimes it is okay to use such method, but during other times we wouldn't want to sacrifice our distributed nature of the system. Indeed, what do you think will happen if one server just goes down? What is the client supposed to do? Of course, it could fall back to other server which is working, but in that case, session guarantees might be just lost. For example, if a client just made the write, then the server failed, and when client falls back, it will not get that write, and the session guarantee will be violated. Let's try to solve this problem by building a system which literally ensures that the definition of read your rights is satisfied. In a nutshell, definition just says that we should read back all writes which we did in scope of that session. So first, let's assign to each write unique write identifier, and this unique identifier, it must be unique across all servers. Also, let's introduce a component which is called session manager, which responsibility will be to sit between client and server, and client will be making requests not directly to servers, but to this session manager. And session manager responsibility will be to track the state of client session and the choosing server which would satisfy a read your write guarantee. Additionally, there are several requirements to the servers, but they are not very strict and they could be reasonably imposed on any eventually consistent system. It is obvious that server must store all the data which is written to it, but additionally there is one requirement that server must also store IDs of all writes made to these servers, and those stored IDs, they are depicted with the red blocks on this picture. Also, the server will have to provide an interface to client, and the responsibility of this interface would be to answer a single question. Given a set of write IDs, server must respond if all of those IDs are present on this server. Session manager's responsibility will be to keep all write IDs which client made within the session It's called write set, and it's depicted within session manager on the picture. And also during the read, session manager is responsible for looping over all servers and asking them whether they have complete set of those IDs. Let's see an example how write flow would work. Here we have client, session manager, and two servers. And the client wants to write 1 to X. So client sends the request to the session manager, and during the write, session manager is responsible for choosing just random server to forward this request to. And in that case, it happened to be server 2. The server 2 writes x equals 1 to its storage, assigns write ID to it, and sends this ID back to session manager. And now session manager's responsibility is to store this write ID in its write set to track it. And then it responds to client that the write was successful. Now assume that client wants to make second write, and it wants now to assign 1 to Y. So it again sends it to the session manager. Session manager chooses a random server, and in that case it's server 1, and the process is repeated. New write ID is assigned to this write by server 1, it is returned to session manager, and now session manager stores this second write ID to its write set and responds back to client. So we have two writes, one was made on one server and another to another server. Let's assume now that the data was replicated somehow from server 1 to server 2, and now server 2 has the full picture, it has all data from all writes, and server 1 has only partial data. So now client wants to make a read, it wants to read X, so it sends the request to session manager, and now session manager's responsibility is to ensure that read your writes guarantee is satisfied. So basically it just sends a request to all servers asking them whether they contain all the writes which are in the write set of session manager. So first session manager asks server 1 if it contains with 1 and with 2. The answer is negative because it didn't replicate to server 1. And then it decides that it's not suitable for the read and asks the same question from server 2. From server 2, positive response comes, and the session manager decides that it's a good server to use, that guarantee will be satisfied, so it just forwards the read to server 2 and sends the response back to client. Now the read-write session guarantee is satisfied, so it's very simple. As you can see, this method works. So basically we achieved a read-write guarantee and client read back all writes which it made. But the problem is that there is an optimality because each server and session manager has to store all reads which are made. And it's obvious that in a system which is used over a large period of time, they will just grow infinitely. And moreover, session manager has to send all this write set to server on each read request. So it's obviously that it's impractical, and so this algorithm is good only for illustrative purposes, just to understand the definition. And in reality, we will use another algorithm based on version vectors. The main idea is that we are compacting all widths, potentially an infinite list, into just a small vector, and the dimensions of this vector will be just number of servers. So in our case, it's just 3 numbers for each server, and 3 numbers needs to be stored on session manager. Each server must have its own clock. Those could be any type of clocks. It could be real-time clock, Lampert clock, or just counters. So the only requirement is that clock value corresponding to each subsequent write should be bigger than clock value corresponding to previous writes. So basically, if we could use just counters which were increased on every write, it would just suit us for the purpose of this algorithm. Each server will have a vector, containing values of all clocks of all other servers. But within this vector, each server will be responsible for updating only one value corresponding to its own clock. And during replication, together with data flow, also those clocks will be updated. So, for example, if server 1 received some data from server 2, then it also receives the clock value from server 2 and updates it in its version vector. Each write has an assigned write ID that has two components. First component is ID of the server where this write was made, and the other component is just clock value of that server during that write. To make it work, we also need to define two operations on version vectors. First, we will say that v1 vector dominates v2 vector if all clock values of v1 are more than corresponding clock values of v2 for the same servers. It basically means that v1 is ahead of v2 in all aspects. Secondly, we need to define merge procedure on two vectors, and for this we just take maximum clock value for each corresponding server. This merge procedure serves for updating version vectors when replication happens from one server to another, and also to merge the write IDs into the write set stored on the session manager. Now, when we know the basics, let's see how it works together. Currently, we will focus only on server side, and what happens on client is not important for us. So, initial state is following. First, all servers, they have no data. Their clock are zeros, and their version vectors are zeros. And also, we have some writes, ordered writes coming to those servers, but they are not at them yet. When the first write x equals 1 comes to the first server, firstly, its clock are incremented, version vector updated correspondingly, and the write is stored in the data storage. Next, second write x equal 2 comes, again the clock are incremented, version vector is updated, and this x equals 2 overrides previous value of x in the data storage. The very similar situation happens when next write y equals 1 comes. Again, the same. Next two writes are coming to the second server. They update variable z inside of data storage. They update server clock and make corresponding changes to version vector. And again, later, two writes are coming to server 1 and make similar changes. By this time, both servers received different writes, and just by looking at their version vectors, we can say that server 1 is behind server 2 and server 2 is behind server 1, because each of them missing some writes. Next, replication happens and data are replicated from server 1 to server 2. And now version vector of server 2 is updated. And now it can be seen that it dominates version vector of server 1, meaning that we can say that server 2 now contains complete set of writes, while server 1 lacks some writes. And finally, the opposite replication happens, and now two servers are in synchronized state, and this is also can be seen from version vectors. Basically, what we just did, we have shown that in order to compare the state of the server and to understand which is more complete and which is less complete, we now don't need to store all the widths of all writes. We just need to have basically two numbers for each server, just version vectors, and that's it. So now let's see how it would work for real reads and writes. Having said all that, we are ready to present a real algorithm for achieving a read-your-write guarantee. So basically, on each write, session manager receives back write ID, which consists of server ID and server clock. And the responsibility of session manager is to just merge these write ID into its write set. And then during the read, session manager must iterate over all servers and find the first server which version vector dominates its write set. Let's see an example how it works for write. Initially, all servers and session manager have their version vectors and write set are just empty, just zeros for all components. Also, clocks on each server are zeros, and now clients want to make a write request x equals 1. It sends the request to the session manager. Session manager forwards it to a random server. In this case, it happened to be server 2. Server 2 stores the data in its data storage. It increments clock and it updates its version vector correspondingly. And it returns back to the session manager confirmation that the write was done together with write ID, which consists of ID of server 2 and the clock value of server 2. Session manager stores this write ID in its write set and the response to client. Next, very similar situation happens when client wants to make the second write, y equals 1. It sends it to the session manager. Session manager randomly chooses another server, server 1 in this case. Server 1 updates its clock version vectors and the response back to session manager, and session manager merges this write ID into its write vector and the response to client. So we have two writes now and two servers which are not in sync with each other. Now let's assume there is some kind of asynchronous replication happened and writes from server 1 are propagated to server 2. Server 2 applies all the writes it received, and also together with applying the write, it receives version vector from server 1 and merges this version vector to its own version vector. And by this time, server 2 has a complete picture, full set of writes, and has dominating version vector. Let's use this state in which we ended up so far as an initial state for looking how reads would work. Client makes a read request to the session manager. Session manager loops over servers and asks them to provide their version vector. First, it gets version vector from server 1 and it checks that it's not dominating its write set. So it discards this server and asks for the version vector from server 2. Now it checks that its write set and that version vector are equal, and it basically means that this server contains all needed writes to satisfy read-your-writes guarantee. And having found that, session manager just forwards that read request to server 2 and forwards the response back to the client. So the guarantee is achieved. Even this algorithm could be optimized. We don't really have to perform all that checks if session managers always prefer one server. So all requests from a client by default should go to one server. And in that case, all session guarantees will be automatically satisfied. But still it will track its write set for the failover. In case failover happens, when we choosing next server, we will apply this algorithm we have just reviewed. And with this, we will ensure that read-your-writes guarantee will be satisfied. Or we could say that it can't be satisfied and the error could be returned to client, but at least client will know whether the guarantee is satisfied or not. To make it work more fast, we could cache the version vectors of all servers just to speed up failover. We have just seen how to effectively implement read-your-writes session guarantee on top of eventually consistent system using version vectors. For this, we introduced component called session manager, which responsibility is to store write set, which consists of basically clock values of each server where we did writes. And during the reads, its responsibility to find a server which version vector would dominate session manager's write set. And for the servers, for that purpose, we need to store only small version vectors and provide them to client upon a request. It is much more effective than straightforward implementation based on definition, which would require storing infinite number of IDs and sending them over the network each time. I also recommend my other video about consistency. It's like more fundamentals and it covers such models as linear usability, sequential consistency, FIFO consistency, and causal consistency. It can be found on my channel. And if you are interested in the implementation of other session guarantees, such as monotonic reads, monotonic writes, write-follow-reads, just watch next videos, which will soon be published on this channel in this playlist. Goodbye and hope to see you again!